All right, so for doing this one, of course, the very first thing we need to do based on yesterday's lesson is we got to get the square root by itself, so that means adding 4 to both sides. So I add the 4, now I have the square root by itself, and of course that means I can now get rid of the square root, which means squaring both sides of the equation. This is the part where we could potentially get ourselves into trouble if we aren't very careful, however, because at this point, when we're doing this squaring, that means we're actually squaring out the x minus 4, which means multiplying it by itself. That is not the same as squaring the x and squaring the 4 on the inside. Exponents do not distribute like we can distribute multiplication. And so for that reason, that's going to fundamentally change the answers that a few of you are getting on this. Because when I multiply that out, I got to multiply everything in the first parenthesis by everything in the second parenthesis, and then we combine our like terms, and we end up with x squared plus 8x plus 16. All right, so now that we're at this point, I have a quadratic. If I'm going to try to solve a quadratic, I can't just take the square root of both sides, so I'm going to end up having to move everything to the same side. So I'm going to move everything from the left over to the right. That way the whole thing's set equal to 0. Now I can look to factor it, and yes, this is factorable. We look for the two numbers that add to 7, multiply to 10. That gives us 5 and 2. And then, now that we have the 5 and the 2, we solve it. So notice that x could equal -5 and -2. But now, this was the very last type of problem that we saw yesterday, where we saw that we're not actually done at this point. Because remember, you'll notice that there was an x in this problem, both inside the radical and outside the radical. And when we see that, that tells us that we need to check our solutions, because there's a possibility that it gave us something a little bit wonky. All right, so we go on to checking. I'm going to check the -5 first. So I plug the -5 in for x in the original equation. Everywhere where there is an x, I plug in the -5, and I only plug in the -5. I'm not doing both at once. We can't do both at once. All right, and then it's just a matter of doing order of operations. So I simplify this stuff inside the square root. Notice that as I do the simplifying process, I'm not moving the -4 over to the other side. This is an impenetrable wall for our purposes here that we cannot cross at all. Otherwise, we're doing algebra, and we might actually end up redoing the same algebraic, not really error, but the algebraic move, which gives us the false positive. All right, so when we check the -5, we end up finding that -3 equals -5, which is not usually true, and therefore we can go ahead and say that that one is not a valid solution. So we just ruled out the -5. Now remember, that's not enough to make a conclusion about the -2. Even with the first one not having worked, the second one might work or the second one might not work. We have to check it and find out. So I plug the -2 in for x once again, and then we check out to see what that gives us. In this case, -2 equals -2. So that one actually works out. So that means that the -2 is a solution here, because when I plugged in this -2, it gave me the same thing on both sides of the equation. In this case, it just happened that both sides were also -2, but that's just more happenstance. All right, so then, as our final answer, we would just say then that x equals -2, and we're done with that problem. Today, we're going to be continuing our work with radicals. And so we're going to start by seeing what all you can figure out when finding radicals of numbers, and doing so without a calculator. And notice I am asking you to do each of these without a calculator, if for no other reason, you might not even necessarily know how to do these on the calculator, because oftentimes doing a cube root on the calculator is kind of tricky. So, figure out what would each of these cube roots be. And so, for instance, as you're working on that first one, we're looking for the cube root of 8. So, in other words, what that means is it's saying 8 to the power of what? I'm sorry, I wrote that backwards. What to the power of 3 equals 8. There we go, now I can say it right. So, what to the power of 3 equals 8? In other words, what times itself 3 times would equal 8? And if you don't know off the top of your head, you could always try stuff. Like obviously 1 wouldn't work, right? Because 1 cubed is just going to be 1. 1 times 1 times 1. So then you might try 2. What's 2 cubed? 8. Because 2 times 2 is 4 times and now the 2 is 8. So yeah, it would be a 2 there. So 2 would be our answer for that first one. And yes, all of these are going to be nice pretty numbers. They're not going to be decimals. So if you're not sure what it is, you don't need the calculator because you can actually guess your way there if you have to. All right, so for number 2, we're looking at the cube root of negative 8. Well, it's the 8 again, so you might be thinking, could it be then negative 2? Would negative 2 work here? Well, what's negative 2 cubed? Let's actually check that out. So if I do negative 2 times negative 2 times negative 2, what's negative 2 times negative 2 going to give me? Yep, 4. That's a positive 4 right there. So then what's 4 times negative 2? Negative 8. So yes, that does work. Because remember that when we do a negative number to an odd exponent, like 3, our answer is going to be odd. So yes, we can go ahead and do that one. All right, next up, number 3. What is the cube root of 27?
3.
Yeah, it's 3. What's the cube root of 64?
4.
Yeah, it is 4. Because 4 times 4 is 16, and 16 times 4, yes, is 64. All right, negative 125. What do you suppose the cube root's going to be there? Yep, negative 5. And so, yes, that is going to be negative 5. You'll notice the numbers inside those cube roots, they grew very quickly. Here we're talking about a list of basically perfect cubes. You know, we talked a lot about perfect squares before. This is actually looking at perfect cubes. They get very big, very fast. And there are a few of them like these that come up often enough that I would expect you to know them. And to be specific, I'd actually like you to be able to know all of these values off the top of your head. Now, some of them you probably don't know already off the top of your head. So this would be well worth taking a moment and writing these down so you can get to know them. Basically, the reason why I want you to memorize these is because they come up a lot. And if you can just look at it and know the answer, you're going to save yourself a lot of time in the long run. All right, so based out of this, there's a lot of little details. So having done this, a couple of quick questions. Let's see if you got it. What is 1 to the power of 99?
99.
1. Because if you multiply 1 by itself, no matter how many times you multiply it by itself, it's going to be 1. And so pay attention to those little things. And then the cool thing is that once you know these few facts, it means you're then going to be able to transition into knowing lots of other facts as well. Because like knowing this, you actually could then be able to more quickly at least figure out things like what's 2 to the power of 8. Because that's just 2 to the power of 4 squared. And if you know 2 to the power of 4 is 16, then it'd be a matter of, okay, do you know 16 squared? A few little things like that will start to build up, and you'll start being able to actually see how to use those facts. Of course, that does remember that you remember that those are the same, right? Do you remember your exponent rules? So let's take a moment and make sure that we do have those exponent rules totally down. These are theoretically very easy questions, but I at least want to mention them before we breeze over this and are using these things in everything else we do. Now, as you're doing these, you hopefully can just look at them and know, okay, I know what the rule is. And you can get your answer. But what happens when you don't remember a rule? Usually what I see people do is they just kind of guess at the rule and hope that it's kind of the right kind of thing. But there are actually ways that we can know for sure what the rule is. We can actually figure out where the rule comes from. Like, if I'm going to do a to the 4th times a to the 7th, a to the 4th, remember, is a times itself 4 times. If I'm going to be multiplying that by a to the 7th, that means I'm multiplying it by 7a's. How many total a's am I multiplying together here? 11. And what did I do with the 4 and the 7 to get the 11? We added them, which you can see because basically I'm just putting them all in a row and I just have to add the number in the first group to the number in the second group. So that's why it is a to the 11th. Now if you can just look at it and know, okay, when I multiply my variables, I add my exponents, great, you remember the rule. But you know, things do get fuzzy over time. We want to make sure we know how to get there. The same kind of thing can help if you hit something like the second one, because even if you know the rule, you might get a little thrown off. Like if you're giving an answer of n to the power of negative 3, that's good but not great, because we actually don't want to leave a negative exponent in our answer. By the way, if you're a little rusty on negative exponents or not sure what they do, we will be taking a look at that in the near future as well. But for the moment, I want to make sure we know how to do this problem. N to the 5th, again, I'm going to show how we can know this out the long way, so that if you don't remember how to deal with it, you can see. So n to the 5th on top, and then we have n to the 8th on the bottom. Why would I do that? Because notice this fraction can now reduce. Because anytime I have an n on both top and bottom, I can cancel those out. And so if I just go through and start canceling out n's, notice all of the n's on top went away. What does that mean is left on the top? Because there still has to be something on the top. Yeah, just 1. The number 1 is going to be left on top. And then on the bottom we have some n's. How many n's do we have on the bottom? 3 of them. And so it's 1 over n cubed for that reason. What's the rule? When you divide variables, you subtract their exponents, which means that that gives you n to the negative 3, and you can see now that n to the negative 3 is actually the same as 1 over n cubed. All right, and then we head on to our last one here, where we have the power to the power. And again, yes, there is a rule you can know, but what if you don't remember the rule? I want you thinking mathematically. I want you being able to look at these and be able to tell what it is and figure these out for yourself. It's amazing how often people know rules but have no idea why they work. I don't like that. You should know why the stuff works that you use. So, if I'm going to do y cubed to the 4th, that means I have y cubed times itself 4 times. Well, notice what that means. That means that we have 4 groups of 3. If there's 4 groups of 3, how many total are there? 12. And what did you do to get that number? You multiplied 3 and 4. Now, technically, looking at the picture, yes, you could add 3 plus 3 plus 3 plus 3, but of course, that is multiplying the 3 by the 4. And so, it is just y to the 12th. Now, again, hopefully you know those rules. If you didn't know those rules, yes, I still want you to know those rules, but please also know where they come from and why these things work they do. It's not just magic. There's nothing about math where somebody just looked down and said, I'll make this up. It's all about just kind of describing what happens when we do it, and that ends up being the rule that we then tell you about. These are all of the rules that you are very well familiar with, or at least I certainly hope you're familiar with them well. But there are some other rules that come up when dealing with exponents which are a bit less intuitive and they're used a little bit less often, like the negative exponent. We saw that touched on, but we aren't dealing with it heavily today. But there's another one. Exponents can be positives like these are. Exponents can be negative, I referenced that. But exponents could be any other type of number too, right? They could be decimals, they could be even fractions. Now, since most decimals can be written as fractions, we're just going to focus on that fraction element. So today we're going to be taking a look and nailing down what happens when exponents are fractions. And so to start that process, please add this into your notes. It's really just one rule, but this second version of it comes up so often that it's worth writing down as well. And so you'll notice this is kind of that big connector between what we've been doing today and yesterday and what we were doing last week as well. Because we were looking at polynomials, where we would have some equation with an exponent in it, right? And then this week, all of a sudden, we were dealing with equations that had radicals in them. Said it was basically the same idea in a lot of ways. And you can see here why that's the case. The radicals are just another way of writing an exponent. So for instance, let's actually take a look at a couple examples here so we can see exactly what radicals go with what exponents based on that. So, like for this first one, and yes, you want to be writing these down as examples. For this first one here, we have x to the power of 1/2. Now, if I just go and use that rule that I was just taking a look at, that means that because there's a fraction in my exponent, I know I'm going to be writing a radical symbol, and I'm going to have an x on the inside. Then, the number on the top, remember, the number on the top is the number that is on the inside of the radical. So that's like going to be x to the power of 1. The number on the bottom, that is always our root. So this one would be like the second root. But that looks kind of funny to me because normally you do not see something written where we write second root like that, right? Whenever that's assumed, whenever that is a 2, that's what we can assume it is if we don't write it in. So we can actually just write square root there because that's what the second root is. Second root is square root. And then it's square root of x to the 1. But of course, what's x to the 1? It's just x. And so we don't need to write the to the power of 1 part. So x to the power of 1/2 just equals the square root of x. And so all of this work that we've been doing, where we've been looking at all these square roots, we have been dealing with an exponent still, which is why in the order of operations, square roots comes into the exponents part. The square roots are the 1/2 power. All right, on to the next one here. You may be very tempted at first to just write this one as the root of x. Let's see here. Which number would be in here? Which one is the radical? Is that the 24 or the 3? The 3, yeah. And then that means the 24 would be here. And this is good. That's a good application of the rule, but it's not great. Because what do you notice about this fraction that I started you with? Yep, they can be reduced. And so whenever you see one of these, if the fraction can be reduced, go ahead and reduce it. What does 24/3 reduce to?
8/1.
Yeah, 8/1, and of course 8/1 just equals 8. And so we don't even need to go into a radical. We can just leave it as x to the 8th. Now, some people get thrown off by this because they're like, but it says, write the expression in radical form. There's no radical there. Well, yeah, if it's just a whole number, then we don't like force a radical onto it. If it's a whole number, then it can just stay a whole number. All right, so then on the last one, we see a fractional exponent. No, it doesn't reduce or anything like that, so we're going to go straight to our radical form. So it's going to be a radical. We know the x is going to be on the inside. Which number is my root here? Is that the 3 or the 4? Yep, it is the 4, which means that the 3 is on the inside. And so this is going to be the 4th root of x cubed. Now, as a little side note here, you notice I wrote the 3 on the inside. I actually could get away with writing it also as the 4th root of x cubed. It just tends not to look quite as pretty, but there's actually some ways that we can use that as well to our advantage. And both ways of doing it have their own advantages and disadvantages. So just so you know, just so you kind of see that down the road. All right, so this is where we start with the fractional exponents so we can turn them into radicals. I'd like us to also be able to do the same thing going the other direction here. So we're going to write each of these in exponential form. When I say exponential form, that means no more radical. So when we see the radical, then we should be thinking, okay, I know for sure that I'm going to end up with x to the power of a fraction. It's just a matter of what goes where in the fraction. What number will be on the top of this particular fraction here? Well, it's whatever number is on the x on the inside. There's nothing written there, so it's assumed to be a 1. So that's going to be 1 over what? Yep, whatever radical it is, whichever root it is. So that's going to be x to the power of 1/3. Okay, with that in mind, go ahead and do the other two on your own before we talk about them together, please. All right, next up, we're going to go ahead and put this into exponential form, so that's going to be x to the power of, the exponent goes on top, the root goes on the bottom, and we end up with x to the 8/4, but we're not really done at this point. Because you'll notice that 8/4 reduces. What does 8/4 reduce to be? 2. So that's just x squared. All right, and then finally, for this last one, again, we're going to go to x to the power of a fraction. Remember that the exponent goes on the top, the radical goes on the bottom, so it's x to the 2/5. And that one's done. All right, you now have a decent idea, I hope, about how to switch between exponential and radical forms. Remember that anytime you see a radical, that just means that your exponent is a fraction. Get that idea down, please.